Hello everyone, I'm Matheus Rodrigues and I'm going to present to you the article entitled A Numerical Approach to Evaluate the Influence of the Piezoelectric Position Layer on the Effective Properties of a Smart Laminate Composite. The co-authors of this study are Humberto Brito-Santana, Reinaldo Rodríguez-Ramos, Volnei Tita, and Ricardo de Medeiros. This is a brief schedule of this presentation, which will divide by into introduction, problem formulation and methodology, analysis and discussion of results, and finally the conclusion. So, smart composites have been awakened the interest of several research to their potential for application in the engineer. So the characters of the constituents, such as the piezoelectric effect because of the active layer and the character of the extrastructural composed layer, like the high directional strength, significant weight savings, and high corrosion resistance, makes this material ideal for some applications, like real-time monitoring, suppress vibration and noise, shape control, and precise position, and that, etc. However, different types of failure mechanisms are observed in this class of composed material. So, at the micro scale level, we observe problems like the border between fiber and matrix, cracking matrix, inclusion, etc. And at the macro scale level, it's common to find the delimitation between two consecutive layers that cause loss in the structural integrity of the composite. These problems call the attention of several researchers to evaluate the effective properties of this damaged composite. This present study proposed to evaluate the influence of the piezoelectric layer position in the laminated composite. So, this is the constitutive relation of the piezoelectric material, and this constitutive relation can be used for smart composites too. Note that we use the effective coefficient in this equation. So the effective coefficient of the smart laminate composite define the relation between the mean of the field variables. So remember that we consider the composite transversally isotropic, so constitutive relation can be written like that. Note that we have 11 independent coefficients. From the multi-scale theory, we can write the mean of the field variables of the RVE is the volumetric mean of the all microscope points that makes up the volume of the RVE. Using the finite element method of discretization, rewriting the average values like that. So, defining the RVE. In this approach, smart composed material can be treated as a periodic arrangement of the unit cell, and if used to represent the properties of each phase of heterogeneous medium, this unit cell is called representative volume element. So, the RVE is the smallest portion of the material that can represent all phases of the composite. In this approach, we can mention two scales. the mesoscale RVE and the microscale RVE. The figure 1 presents this RVE. So, in this study, we work with the RVE of the figure 1A. This. And this RVE are composed of the laminate interface, 8 structural composed layers, and a piezoelectric layer. This make the mesoscale RVE. So figure 1B represents the periodic smart composite structure formed by an arrangement of this RVE, and this figure 1C represents the microscale RVE, where 1 represents the matrix and 2 represent the fibers. The model in the mesoscale used in this work was previously presented by Brito-Santana. So, to ensure the continuity between the adjacent areas, for example, no gaps or interpenetration between two consecutive areas, periodic boundary must be applied. It can be noted that for any regular RVE model, the displacement of pair of opposite faces are described as this equation, where V represents the periodic part of the displacement component, that is, local fluctuation on the boundary surface, and the index K corresponds to surface of the RVE. Displacement fluctuation is periodic on the boundary of the RVE. So, periodic boundary conditional ensure that local fluctuations are equal for opposite faces. Thus, the difference of displacement in the boundary is like that. So note that the right side of the second equation is constant because the macro strand is null, and this is the size side of the RVE. The same concept can be applied for the electrical potential condition. This periodic boundary condition can be conveniently applied in the computational model as presented by the Medeiros. 3 analyses are needed to find the shear effective coefficient. So, from the constitutive equation, we can eliminate the specific rows of the matrix and can get the coefficients from these equations, these 3 equations. Now, to define the lamination, we use the parameter theta. This parameter does the degradation of the interface between 2 consecutive layers in the mesoscale RVE. This model of the lamination previously presented by Brito-Santana. So, 2 cases were considered in this analysis when theta is equal to 1 and when theta is equal to 0. The theta equals to 1 implies a total separation between 2 consecutive layers, and theta equals 0 implies perfect contact between 2 layers. For the numerical analysis, we use 20-node 3-quadratic isoparametric hexaedral piezoelectric elements, Abacus software, and a mesh refinement study was carried out to evaluate the convergence of the numerical results. The mesh chosen for the analysis have approximately 5,500 elements and show good convergence. As previously mentioned, the delamination is located between the first and the second layer. The properties of each material used in this work are presented in the table. All properties have been retired from previous studies. For the case study, we used the 9-layer RVE presented with this state sequence. 54 analyses were performed, 3 for each position of active layer, that is, 27 for intact interface and 27 for the laminated interface. So after this, the computational homogenization procedure was performed based on Python language routine. Figure 4 shows the shear effective coefficient found for the 9-layer RVE for each position of piezoelectric layer as a function of the degree of the delamination, 0 and 1. It is possible to note that the last coefficient C66 related to the shear strength tends to 0 when theta is equal 1. This behavior was expected to the loss of their stiffness caused by the delamination interface in this direction. The coefficients C44 and E15 present a very small variation regarding the degradation of the interface because of the direction of the sharing applied. And the coefficient E15 presents a small decrease when the active layer is in the first position. And through figure 5, it's possible to observe the variation of each coefficient as a function of the piezoelectric layer position. Note that the values are normalized. Thus, RC44, RC66, and RE15 represents the region between the effective coefficients analyzed and it's the maximum value obtained in each configuration, intact or delaminated. So, the effective variation between the highest and lowest value of each effective coefficient to the piezoelectric position layer with and without delamination was calculated. Regarding the maximum relative difference, it's observed that the all shear coefficient showed a variation of less than 0.3% and less than 0.15% for RVE with delamination. Finally, this work allowed an analysis of the influence of the piezoelectric position layer in RVE. The last coefficient, C44 and C66, lose the character of symmetry about the variation of the position of the piezoelectric layer when the RVE is subject to delamination. The position of the piezoelectric layer in the RVE has a little influence of the value of the shear effective coefficient. I acknowledge the financial support of the Santa Catarina State Research and Innovation Funding Agency, FAPASC, and as well as Coordination for Improvement of High-Level Personnel, CAPS, the Programa de Bolsas de Monitoria de Pós-Graduação, PROMOP, and the Santa Catarina State University, and finally the National Council for Scientific and Technology Development, CNPq. And